Splendid. Welcome back. Welcome back. So, first things first. Bomb lab. How did it go? Was it fun?
Yeah.
Yeah, very lucky. Was it too fun? No. I've had people that say I didn't know nothing else. Was it difficult or was it informative? Like, give me some.
I think it was really hard at first once we figured out how to use GDB.
Yeah.
Yeah.
Yeah. No, it's
But then there's really a pattern.
oh yeah, and stuff to see like, oh, put in breakpoints, step through, see what's happening. A little bit of a deep dive, right? But now you're more familiar with assembly, right? So it's becoming more of a friend. Good, we'll be doing a lot of assembly for a few weeks. Yes?
So, for two of them, I used a very, weird method. I just kind of wrote up the registers because I saw, what its values were checking. I was wondering if you could go with actual patterns, because
But why you're seeing the patterns?
no, I didn't see any, so I kind of just got the answer by, physically seeing the code.
Yeah.
And my numbers were pretty low, so it worked for me.
So the thing is that the intent is for you to just kind of go through the assembly step by step and kind of do the work as an automaton.
Oh, okay.
You could be like, oh yeah, there's a lot like Fibonacci. Anyone? No? Everybody has a unique problem, by the way. So we all have different problems to solve. So some people may have had a Fibonacci sequence in there somewhere. Yeah. Pick one person again. So we can go over things, but the things that, so what we're going to be doing, we're going to be finishing off assembly today, get it all over with, and then we're going to go into actual exploitation, where we're attacking a program, then we'll have to use GDB to do stuff. So we'll gradually learn more about GDB and the style and so forth. So this is kind of more like me just pushing you into that swimming pool, holding your head down, and then and so, yeah. That's what I do. So the next lab that I'm hoping to release tonight or so is going to be called Prof lab, which is similar structure, so there'll be a scoreboard and so forth. Except the point there is that you're supposed to exploit the program. And they'll be guided along, there'll be a document that goes with it. And those are the two very structured labs. So the remaining labs are just going to be write an exploit against this thing here. Yes. But you'll be ready by then. Yes. Yoda says. More questions? Yeah.
I mean, it's not a question, but it just took a while to get used to Intel syntax from the 255. So working on Motorola to switching to.
You were used to Intel syntax, or?
Used to Motorola, the.
Oh, I see. Yeah, we're using AT&T syntax, by the way, in the slides and also in the assembler.
No, to switch over, because Motorola has D1, D2, D3, and then.
Yeah, so there's three different things here. There's the Motorola assembly, and then there's x86 assembly from Intel, and there's the Intel syntax for that, and then there's the AT&T syntax for that. We're using AT&T syntax for x86, and you're saying that's different from Motorola, and that's confusing. Yeah, it's a difference in field, right? Different structure.
So it just took a while to get.
You're used to RISC assembly, effectively, which is a reduced instruction set, so there's only a handful of things you're supposed to be able to do. There was a huge debate, people were at conferences bashing each other's heads in because no, RISC versus CISC, complex instruction set versus reduced instruction set. As it turned out, all the reduced instruction sets ended up being really complex at the end. And all the complex ones started to incorporate into staff all the things that are, so they kind of converged to the same spot, but people still have bruises from that era. Now everybody kind of uses x86. Apple folded their own architecture away, and now they just use x86 like almost everybody else. So Intel was like, yeah, we just own this market. And then mobile phones came along with ARM, and now Intel is scrambling to do stuff. It's really funny. So, anyway, any other comments or questions? Yeah, okay. Let me just look at the scoreboard, and just to celebrate you guys a little bit here. Oh, goodness. Box, plot, whatever. Okay, bump. Sorry. I've made it so hard for me to do not this work. Try time. So, I told you there were 6 phases. Yet, almost the majority of you have solved 7. Good job. Yes. Secret phase. What do you think about the secret phase? Was it fun? It was easier than something else? Yeah, okay. I actually shuffled them for some people. So it may have been that the hard phase ended up being phase 4 for some people. Sorry. And yeah, 666 and so forth. We decided on a policy where for every 24 hours after the deadline to begin, you lose 15% of your grade, but you can still submit. So if you guys are late, or if you have special accommodations, this is still open. So if you want to spend a little bit more time on it, that's fine. If there's somebody who's like completely had no idea what was going on over here, I have office hours at 1, then come talk to me. Or in general, if you have any questions or something that you think is, needs to be explained a little bit better, happy to talk to you guys. So let's get back to track here. Let's talk about some stack stuff. So this is something that by now you guys are so intimately familiar with from your explorations into binary bonds that you already know all this stuff. But anyway, I'm going to review it now, given that you guys learned it. This is the stack. And remember, we talked about this kind of weird locker analogy that I was really proud to present to you guys because I went through the effort at some point to make slides for it. Not that it makes any sense, it's just that I have the slides and I was like, cool, I'll use that. Here's the actual thing. Here's the actual way stack is structured in x86. So remember one thing, that it grows down. It's the Australian stack, right? It's like, I want to add something to the top of my stack, it means that I'm like shoving it in this direction. So it gets a little bit confusing, but bear with me. Now, at every point in time, we have this register ESP that's pointing to the next thing that we could be doing, right? It's like the lowest word on the stack is what it's pointing to, okay? Which means that if you wanted to like get some more space for one of your local variables, you would need to subtract from ESP or RSP or whatever it is that you're using. Make sense? And if you want to release your stack frame to go back to another place, you increase, okay? So let's have a quick look here. There are some built-in instructions in x86 that accommodate this kind of stack behavior that's used by C and other languages. So they include things like push, right? That's what stack before. You push on them, you pop on them. So if you want to push a word, you would say push L, which is a 32-bit word. You would say tell what register you want to push onto the stack. Or if you want an immediate value, you can also put that right on. And what it does is automatically decrease ESP by 4 and shove in the bytes that you specified in your source on the top of the stack. Makes sense, right? And then, of course, we have pop, which does the opposite thing. And when you say pop, it means that we're actually taking the thing and we're putting it back into a register. So there's like a, you can say pop L, and then what register you want the data in, and you've gathered it back. You will look at this and be like, that's very interesting. Probably not going to use this for a while. Then later the person will be like, oh my God, I'm going to use it so much. And this is going to be very pivotal to some of the shell that you're going to be writing. So that'll be fun. We also have this thing that this is a word that I'm going to be using over and over. And the reason why I'm using it is because it defines the class of vulnerabilities we're going to be talking about. It's called control flow vulnerabilities. So remember that when you structure a program in C or in assembly, you have data on your stack, but you also have some things that are not part of the program's data. They're part of its control flow. Like what? What do we put in the stack that's part of the control flow? The return address, right? So it's there, bundled in with all the stuff that you're using. You're shoving in your like Pokemon Go achievements and stuff and putting them on your stack. And then you also have this like return addresses like intermingled in between. So if your like Pokemon Go character is too big or something, you might hit some of the other stuff. I'm being present here of those things that we'll encounter. So that is actually the fundamental mistake, if you like, in the design of this architecture here, is that we're taking data, substance from malicious users, and control flow that the computer needs to be able to operate properly, and mixing it together. And that's just a recipe for mistakes. Right? We will see this come up again and again in different designs, including the web, where you're like, oh look, it's like it's the person's name happens to have an HTML tag inside of it, or JavaScript. Yay, right? Oh look, it's a PDF. Oh, it has it. Takes over your computer and eats you, right? So there are all these things that can happen. So this is an example of a control flow vulnerability. So what is control flow? It is this methodology of saying, hey, I want to be able to be in some location of the program and call a procedure or a function or method or whatever you want to call it. Okay? And come back without having everything changed, right? It's really boring to go through a program and everything is just jumping here and there and so forth. We want something a little bit more flexible because that's how we think about programs. Imperative programming is about you do stuff and then like you abstract away this notion of like, hey, I want to call and get like a square root of something. Or I want to call and print something out. And I want to come back to where I was. That's what the call is for. And you've seen this now in your bombs. You're like, yeah, okay, I can call this and that. Yeah. So how does call work? What would call need to do? You know, I want to call some part of my program and then I want to get back. What do I need to track to be able to do that?
The address of the first line of that program that pushes into the stack.
Yeah, so there's two things. I need to be able to specify where I'm going, and someone needs to be able to track how to get back. And I think that's what you're articulating, is like, I need to be able to know that when I'm done going to this address of the program, I must return to here, right? So this is the return address. So in fact, call pushes the address of the next instruction onto the stack. So there's an implicit push operation involved. Also know that if you wanted to, for instance, know where you are executing in a program, you can't just type move EIP into some register. That operation doesn't exist in x86 assembly because you should never be able to use it. There's no wasted silicon of being able to take EIP and move it into register. The only way you manipulate the instruction pointer is through things like call and return and other things that are specifically designed for control flows. Make sense? Some people looking away, like I look at them and they're like, I suddenly saw something on the wall. People okay? People not okay. I'm so confused right now. I'm okay? Good, okay. Oh no, what have I done? Okay, let's resume this. So notice the, this because some foreshadowing over here. Let's look at the binary code here, like the hexadecimal code behind the call operation. What do you notice?
Four zeros on the end.
You notice there's 4 zeros on the end. Yeah? That may come up later, in fact. But where is this address in this instruction? Like, how does this instruction know that this is where it's supposed to go? Telepathically. Yeah, I know my path. Let's go over there. I want to do some theories.
Displacement?
Displacement? So what does that mean?
Go forward or backwards.
Ah, so it's relative to what exactly?
The pointer now.
Yeah, and where are we now? This classroom, in this program, where are we now?
854E.
Yeah, so we must have been executing this instruction. So it takes instruction if I add this number, this looks like a big number. What's happening? Doesn't it, like, here's the E8, which means call bar. And here are these 4 bytes, but like, look at these bytes. It's subtract, but like, look at it, it's like 0804, and I want to end up in 0804. Yet it looks like the number that I'm subtracting here is gigantic. Doesn't it? Dilemma. What? Explain. Say again?
Is it 3D times 6 that you add?
3D times 6?
Math
Oh,
my head well.
it would be so interesting. It's just like, yeah, no, it's like, you take the integral of like all of that. Yeah. Make it as easy as possible. Complex instruction set. Yeah, exactly. Yeah, it's very easy. It's the coefficients of the Fourier series of this epsilon. No, but I mean, the thing is that sometimes that's the answer, something like that. You're like, of course. It's not the answer though.
Backwards.
Ah, yes. Always think that things are backwards when you're looking at assembly. They are. In fact, it's exactly backwards. If you look at it, the number is actually in little endian. So the number itself has a most significant byte of 0, 0, 06, 3D. So if you look at that number, now you want to look at the current address over here. Suppose we actually look at it relative to this address over here, right? Now let's add 3D. Anybody can add 3D here? Compare it to this address over here. You see? Done. Okay.
You need to do math over here.
Here, no, I'll do it even better. I'll save us the trouble and just show you how to do the math so that you never have to. Let's go into machine here. Da-da-da-da-da. Reset session. We can try it in so many different ways. We could use Bash, we can use Python, we can use PC, we can use the built-in Microsoft calculator. Let's use PC, Embase 16. So I'm going to type in 08048553 plus OX, what is it, 0000063D. Oh, great. Base 10. 10 is now 16, given that I changed the base of my thing. Oh, look at that. Look at that address. Doesn't it look familiar? Yes. Of course, you are all required to do this in your heads for exams. Oh no. Did that make sense? I just added the numbers. Right? Just imagine you had like 16 fingers, right? And you were just counting, and you had always done that, then that would be very easy for you, right?
Why I-based versus O-based?
Oh, sorry. Yeah. This is called BC. It's like a binary calculator. I-based just means like the input numbers that I'm going to be specifying here are going to be base 16, base relative to the base I'm in right now. So now like the world changes to everything you type in is hexadecimal. So if I type in F, it's like, oh, 15. But then when I say like, I want the output base to be 16 as well. Except how do I type 16 now that everything that I typed is hexadecimal? I have to say 10, because that's 16 now. Sorry. Let me try a different way of doing this, because this is maybe too complex. Look, we have a calculator built into Bash. 2 plus 3 is, that's what I thought. Okay, OXF, oh, so we can do OX 08048553 plus OX 063D. I would always use BC here. Here we can always use base 16 and then type it in. Sorry, this is cop-out. I don't know how to make Bash return something in hexadecimal. Sure, it's possible. Does it make sense? I just showed you how to use a calculator, so let's get back on track. So, why would we want to push EAX after this? Like, what significance would EAX have at this stage? We had a special contract for this register. It's the return value, right? So return address now has already been popped on, so it was pushed by call, and then the last thing that did was that call the process over there in main called return. So it actually popped on. This stuff just pushed on. So now we're actually in an identical state as we were before, except EAX now contains the return value of the function. If it's a function that returns anything, it will be stored in EAX. Make sense? So that will be now the return value.
What if it returns to two values?
Yeah, we don't do that in C. We left it at 1. If we're in Python and all things like that, what you're returning is a pointer to a structure that contains all the values and tuples and whatever.
So can it also return addresses or just values?
It's always, I mean, those are interchangeable. It's a 4 bytes of whatever you please find that stuff, right? You can interpret this as an address, interpret it as an integer, whatever it is. We also have a concept here that, like, for instance, the function here would be allowed to mess up some of our registers. And there's like a set of them, and I'll get to that later in the class, that you can mess up. So like if you really want to keep those values, you would have to just push them onto the stack ahead of time, and then pop them off just to make sure they haven't been right. And there are some registers that these functions over here are not allowed to touch. So they themselves have to save them onto the stack at the beginning of the call, and then before they return, they pop it back up, right? So we're trying to do as much preservation as we can, right? Save the registers. Okay?
And what does that? Like the compiler? The compiler inside?
The compiler, yeah, I mean, all assembly code that you'll be seeing in this lecture, and for the most part, has been generated by a compiler by taking the C program and all the conventions around how C compiler should be, or like how C programs should be run by a CPU, and getting into the right assembly that corresponds to all the protocols, like save these registers, put in a call operation, save it to a particular memory, it does all this work for you, right? So after you type your GCC thing and so forth, you'll end up with a compiler that follows all these rules. Now, it's very interesting to think about how do you make a compiler like that? And that's the subject of a completely different course. Okay? It's kind of fascinating to think about how do you write a compiler in steroids. It's super optimized. It's kind of like it was really, really cool in like 1970. And there's some people who still think it's cool because it's kind of cool. Like, how do you compile yourself? Oh, that's cool. But those people are in prison, or like they're high somewhere. Anyway, we have the corresponding thing for a call here, it's called the return. So rect. All it does is pop off the address from the stack and jumps to it. So if I want to change the EIP, what can I do? Tell me how I can change the EIP in the program right now. I want to change it to an arbitrary address. I want to change it to the hexadecimal address OX dead beef. This is where I want to go.
Which is on a
What do I do, sorry?
which is on a slave,
How do I do that?
and with
How do I do what operations do I type to get this done? Push, and then this address over here, and then ret. Does that make sense? Ret has no idea it wasn't an actual call operation that saved it on the stack. It's just like, oh, there's something on the stack. Takes it off and then goes there, right? Moves it into EIP. Yes. Cool, okay, so let's take an example of this study. So this is the same exact snippet of a program here. And we'll look at the memory here as being in blue. And we'll look at progression kind of happening from left to right. And we have our instruction pointer at exactly the address that was executed. So when we do the call, what happens? We push this following instruction over here, the one ending in 5.3, onto the stack. The stack pointer has been decreased by 4, because it's a 4-byte address. And the instruction pointer has to change to whatever it is someone wants to call. Or it takes the next address and it adds the offset that you specify as part of the call. And that's your new EIP. Make sense? And then when you want to return, you turn to the converse. You add 4 to ESP, and you choose the EIP to correspond to the address that you saw here on the stack. Okay? Notice how there's no cleanup. Because why would we clean up, right? It's like the 1970s philosophy. It's like, we're having a picnic, we'll just leave the stuff. It's like, so you're like, actually your stack, if you have a long program and it runs stuff and that, runs up and down and returns, you actually have a lot of old stuff in your memory. All the old stack frames and various crud on. Why? Well, because hopefully you architected your program well enough that you're never going to run into any problems with it. And hopefully you remember to initialize buffers and so forth so that you don't run into problems. Of course, that's a big maybe. It takes a little bit of time to clean it up, honestly. You have to call operations that are like pouring 0 bytes all over your stuff. In terms of secure programming, there's a lot of very interesting information that you can lean into if you're able to read stuff that's left over on the stack frame. You can learn a lot. And we'll get to those later in the course. Anyway, so when we talk about these, how to use this call operations or return operations, we're really talking about a philosophy of how do you create programs. So the reason why we have this layout right now is because you technically could look at a program and say like, hey, I know exactly how deep you're going to go. I know you're going to at most call 5 functions and then go back and so forth. And you could maybe like Maybe I'll just have a little buffer that says exactly how far you've gone. You could think about taking up a few registers and be like, you called this function and then that function and then something else. It all becomes very tedious and breaks once you start to think about recursion. Just like everything, including your mind, breaks when you think about recursion. Everybody's mind is broken already? Oh, they're like, oh yeah, that again. If you want to support recursion, you actually do need to have a stack, because you don't know how often things are going to be called. If you wanted to infer how often it will be called, you'd already be implementing recursion, so it's recursive. Amazing. So code, in general, in these types of languages that support this, needs to be what's called re-entrant. You need to be able to kind of execute it, and once you arrive inside a function, you need to be able to have the same view as if you had been called from any other place. So the same call can be called multiple times, and this call and return pair enables you to just have the same visibility every single time that you go into it. So as a part of the deal, as part of the call and pop, we often need to provide some environment, some information to whatever we're calling. For instance, like, it's rare to just call a recursive procedure just for the hell of it, right? You tend to call it because you're computing something, or hopefully you're doing something interesting. Like, I want to find the next Fibonacci number, or whatever. Which means that it needs input. It has some parameters, some arguments. But so far we haven't really talked about how that works. We've actually seen it before, though, in our previous lectures, how arguments are used in C and in those re-entrant languages. Do you remember what we do? If I want to call a procedure and we're provided two arguments, what do I do? So definitely I need a call at some point, but I need to provide it two arguments. What do I push it on the stack, right? In reverse order, actually. So that AEBP for that method is the first argument, and 12 is the second one, and so forth. Right? So just push them up the stack. Then, if you think about it, that enables recursion really seamlessly. Because I can just keep pushing arguments up the stack, keep pushing, doing the call, and have like a huge chain of stack frames that are corresponding to the computation I do. And if I'm calling recursively too many times, eventually I'll actually fill up all of my stack that I have, and I end up with what's called stack overflow. So if you've seen stack overflow something in programs or games when they break or something, you're wondering what on earth that is, that's what that is. Right? Unbounded recursion, or somehow the number of stack frames that you ended up with was greater than the amount of number you allocated to that. Okay, so then we have some, like, of course, rules of discipline here. So the intent is for stack frame to be this ephemeral, this temporary state of the program, right? It's like local variables, like a buffer, and you shove something in, you do it, and then you're done with it. You don't want to use it again. It's not a global thing that may be used later in the program. It's just something that's just you doing something dirty right now. So we have particular rules about this that I mentioned just earlier, which are that when you call something, so the way the stack builds up is that the lowest stack frame is the one that's current, right? We're never modifying something of an earlier stack frame. So we have like EBP and ESP, and that is our world. And if we want to look at arguments, we know exactly where to find them, and that's kind of it. So if I am done with a particular instantiation of a method, I need to clean up the stack frame before I proceed. So that's the content that we're entering. So this ends up with something looking a little bit like this. Suppose you have this little program, it's really stupid. It has a little method here called you who calls who. So you who, and then who calls am I, but it does it several times. And then am I is this ridiculous program here that's recursive. So let's look at what the stack frames would look like. So you have a call chain that's going to look like this. You is going to call who, it's going to call am I twice, but not at the same time. It's going to call am I, and then later another am I. And each of these am I is going to call itself, so you're going to end up with another stack frame. So the way it would kind of look like is in terms of several frames here. So if this is the top of the stack over here, we're going to end up with delineations of different environments for all these different procedural calls. So suppose we are in a particular procedure called proc. then we have our stack pointer. It's the current thing we're doing, so we know the stack pointer is at the very base, or at the very top of the stack. We know our frame pointer is pointing to where we started, right? So everything between EBP and ESP is our local variables, right? If I wanted to add one more, I'd just call push or subtract from ESP, and that enlarge the stack, right? So this also means that for every single procedure, you have the setup code and the what's called the epilogue. This is something that we saw last time, but we kind of skimmed over. So what it's going to do is that it's going to try to create an environment that looks like this. It's going to create, it's going to have a stack from here where it has the base pointer, it has the stack pointer over here, and then it goes who, so it changes both EDP and ESP. And it keeps going like this, up and down. There's an Ymir, here's the recursive call, just having 3 different stack frames, let's keep going. And now this sub process here is done. So it's going to clean up. So it moves the EBP, pops it off, and then it gets the old EBP, and now the ESP is in the right place. So it does it again, and again. And now this guy here calls some different method over here. It's MI again, and goes back, and all the way up. So it's just like, this is the intent of the stack frame. So we'll look at this. So everything that's in the call over there, those are local variables for the stack. Right? Not depicted here are the return addresses. Actually, where would they be? Return addresses, if you look at this layout over here. Yeah. Yeah, so somewhere there's going to have to be return addresses in between these things, right? So are they part of, where do they go?
At the EBP.
So we're showing this EBP over here, and then like the next address above it is the return address corresponding to the return frame. So it's always this pair. And we're going to see these pairs a lot in this course. Good. So if we dig into it a little bit more, so this is where I was just saying, we have this caller frame, the method that called us, or summoned us somehow. It has a set of a bunch of arguments over here that is for this procedure that it wants to call. Then it pushes, it does a call, which pushes the return address onto the stack. And the first thing that the new method is doing is to what do we do? That's the first thing that we need to do if we want to set up a. We're in like a new new method, new procedure. It's like brave new world, and we want to like. It's like cool. I'm gonna like raise some money, have some kids. I'm gonna set up a stack frame, right? There are all these like glorious features that you can do. So how do you set up a stack frame? It's to push. We're about to modify EBP, right? And we need to have some means of getting it back, so we push it onto the stack. Right? And now we're like, oh cool, and now I'm gonna get some money, I'm gonna like create some like big like glorious like 2,000 byte buffer or something for me, right? So you just subtract something from ESP and you set up a stack frame. Right? Now like you could be like, oh I'm gonna call some people, right? And then you could call, you create another stack frame, and so it continues, right? So on your below your stack frame, you're gonna have the old frame pointer right here. You're gonna have saved register, for instance, like, oh, I really, really want to modify EPX. And I know I'm not allowed to because somebody else might be using it. Somebody in this green or whatever color this is, this undefined color up here, stack frame, is going to use EPX. So I'm going to push the old value into the stack before I start modifying it. And then later when I'm done with this thing, I'm going to pop it back off. Okay? And then I'm like, oh, here's my buffer and my integers and my whole family of variables that I'm playing with. And then eventually, I'm going to be like, yeah, it's time. I'm going to call someone. I'm going to call another process or other procedures and like that. So I start doing the same thing. I push the arguments in reverse order into the stack. I do a call. And then I just like, oh, hello, I'm alive now. I'm going to push EBP into the stack, and I'm going to create some variables. It's going to be fun, right? So that's the natural progression of things in Stack Lab. We'll do that. Sounds like a terrible movie. So this is kind of what it looks like. By looking at this, what does a frame pointer always point to? if you like, you're now in GDP and you're looking at it and you see a like you see a frame pointer value. What does a frame pointer always point to? Which contains what?
The old frequency.
So a frame pointer always points to an old frame pointer. Right? This will prove immensely useful. There's just it's like a movie. I'm doing all this like foreshadowing elements. You guys are like, oh yeah, I got this kind of like weird device like I used in the movie, serves a particular purpose on it being a plot device, but this plot device will come into handy later when it saves the day. Frame pointer will be very useful for performance string exploitation and things like that. Cool. Okay, so frame pointer, let's point to another frame pointer. Very cool. So now we know what's inside a stack frame. Let's look again at this swap procedure here. So here we have a little method here. It's called call swap that just sets up all the arguments for this familiar routine over here. Remember what swap did? Two pointers, takes the values that they point to and just switches them around. Let's look at how this would look like in execution. Okay? So if we look at what call swap is doing, it does there a sub 8 ESP. What is it trying to do? Create space for what? Two local variables, but it's using them as parameters. It's like arguments for the swap routine, right? It's just creating. It's like, oh, I need 8 bytes here, and then I'm going to be shoving into these 8 bytes 4 at a time the 2 parameters that I want to specify for call. Okay? Alternatively, how could I have done the same thing? Move into registers. Well, in 32-bit assembly, we're expecting this to be a part of the stack pretty much. In 64-bit, we actually expect it to be a part of registers because we have so many. So if we wanted to be a part of the stack, how could I have written this green part over here differently? Yeah, we just pushed it, right? Why not? Just push this value and that value, right? Equivalent. It's just that assembler here decided like, oh, I want the program to be aligned at like 16-byte boundary. So it means I'm going to take a slightly longer assembly routine to do this so that I end up with the right alignment because it's better for cache and all sorts of things like that. It's doing weird considerations that is completely non-fault. But that's the reason for some of the weird stuff you see in there. So what's happening to the resulting stack? Here we had our stack pointer, and we decided to subtract it by 8. So now we're down here. And now I'm shoving into 4 ESP, which is, I decreased it down into here. 4 ESP is up here, course 2, so this address over here. And this ESP is right here. And now I do a call swap, which does what? Pushes the return address into the stack and changes ESP, so ESP is found down here. So I end up with this resulting stack over here. Yeah? Cool. And now if we look at what swap is doing, remember we looked at this before. We can analyze what's going on here in these registers. Let's look at this setup and this finish part. The prologue and epilogue of this call. What is happening here? Push EBP? Creating a new stack frame, so we're getting a copy of the old EBP because we're just about to modify it. And how do we modify it? Move ESP to EBP. What does that accomplish exactly? I move ESP to EBP, what have I done? I'll create a new base of my frame, right? Now I have like the smallest stack frame in the world, right? There's nothing in it. And then I'm going, it's really tight, I need bigger, more space, right? So you push EPX, well, you could. Here we're not creating any significant stack frame. The only thing that we put onto the stack frame that's not EPX or EBP here is, said already, EPX. Why do we push EPX into the frame? It's one of the, no, all the parameters are stored here. We're going to modify EPX, and we're not really allowed to. Our parent function is going to be really mad if we modify EPX. So there's the notion of caller state registers and callee state registers. So in order to prevent us from messing up EBX royally for whatever computation the parent procedure is doing, we push it onto the stack. And then we do all sorts of magic, and we use EBX, and we're really happy. And then when we're done, we pop it back up, because it's the next thing to the stack. And now, at this particular moment over here, where's ESP and where's EBP? They're pointing to the same thing, in fact. And they're pointing to what? They're pointing to the old frame pointer, right? So the old stack frame I want to get back, so we do a pop operation, which decreases ESP by 4, so now we're putting in the return address. And EBP is now whatever value it was previously. So we're back into our old stack frame, except we have a return address, and then a return. Which pops that back off, changes ESP, and we're back to the way we were, right? Happy dance. Yeah! Yeah, it's so cool, right? Yeah. This is how your computers work, or your phones. Oh, it's how your phones work. Look, this new generation. I actually taught someone who had never used a laptop not so long ago. They were like, "What? I've had an iPad my whole life." I'm like, I'm so old. Yeah. Okay. Anyway, so this is what it would look like. Let's just animate it a little bit. So here's our push operation. We have here's our stack when we set things up. We talked about how this was set up. We pushed these two arguments. Actually, we didn't push. So we moved these arguments onto the ESP and for ESP, and push the return address. And now we're entering swap, right? So what happens? We push the old EBP onto the stack, and notice how that EBP over here is pointing to some stack frame up there, and ESP is pointing right here. And then the next thing that happens is we move ESP to EBP. So EBP now points to what ESP is pointing at, which is right here. So this is the tied little stack frame over here. And then we push EBX, so now ESP is down here, automatically because of push. And so we have the old BX value here, which is what we're about to modify. We have our new frame, everything is happy here, right? We do all sorts of stuff. So what do? Remember this from before. We get the two variables. So how do we get the variables? Well, it's always 8 EBP and 12 EBP, which now makes sense, right? Because we know that the frame pointer is here, and it must get past an old, it must get past the old frame pointer and the return address, and then end up in the last arguments pushed onto the stack. And then the next one over here is 12 bytes away, and so forth, right? And then we do all our stuff, and then finally, when we're finishing up, we're going to be in a situation where we pop off the EBX over here, so here's the EBX, and we pop off the EBP, so here, sorry, here's the situation, we pop off EBX, we pop off EBP, and now ESP is pointing to a return address. Return. Here's the thing, here's the caller save and callee save. So we have to save EBX, but we don't have to do it for EAX. In fact, we're expected to modify EAX, and it's just like a void function. And ECX and EBX we can modify as well, so if the parent function wants to keep those, it has to push those things onto the stack itself. Yeah. Okay, so here's the full disassembled swap. Now at the beginning of the course, showing you a slide like this, you'll be like, where am I? Why am I here? Right? Why didn't I choose econ? Or whatever it is that you were thinking, right? But now this is like, oh, firmly makes sense, and you're like, oh, this is so cool, this is my new life. This is what I do, I look at these numbers, and it's fun, right? And so you can go through this systematically, kind of in your like GDP in your mind, and it will make sense. Was that just like a, you just have a knee-jerk kind of reaction of like, ask a very short question? Okay. Anyway, so this is just the So now we talked a lot about instructions. We talked about how memory works. Talked about a whole host of things. Right? Any questions so far? We feel kind of well versed now, right? So let's look at a little bit more at these stack frames. What's a local variable, really? Okay. So if I wanted to allocate some memory for an integer that I'm using that's not in a part of a register, or even like a little byte or something, I may end up subtracting something from my stack pointer. So imagine this is the code. We have here a code called add3. It's the most boring code you could probably write, and completely bloated, because its only purpose is to add 3 to some number. I have no idea why that would be useful. But suppose this is what you did, and you said here, hey, I want to have this local variable here called local x. It's a copy of the input variable, and we know it's 4 bytes long. And then let's look at this assembly. And what do you notice? Yeah, it's being completely spurious. It's like an Enron executive, right? It's just like, hey, let's just get 24. Why not, right? It's like the first rule of government spending. Like, why buy one when you can buy two, twice the price, right? So yeah, we decided to arbitrarily allocate 24 bytes for our 4 byte thing, right? And sometimes that makes sense. Often it does not. It has to do with alignment and other things that the compiler is thinking about. But there's actually a little bit more that's happening here. So it's using part of this for some other stuff on the stack. So let's have a look at what that is, right? Notice how it references this variable. Now, we have a choice here. We could say like, hey, I want to reference this local x variable as being something relative to my current stack pointer. Actually, what would I write? If I wanted to make it relative to my current stack pointer, how would I reference local x? Oh, look at my wrist. Oh. So 24 bytes above ESP, we know we have EPP. Did I hear EPP? Okay, there's a lot of echo. Hello. Okay. So it must be 20 bytes away. So I could say 20 parentheses ESP, and I would get access to it. Yeah. Okay. Good. Or I could go the other way. I'd be like, hey, I have this frame point over here, which is kind of pegged here at the very bottom of the stack frame. Remember, this is Australia. So 4 bytes away from that is my local variable. So if I say here, hey, minus 4 EBP, I'm referencing local x, right? So when you see this in code, it now makes sense, right? Okay. Anyway, so let's look at some other things. Here's the call that it's making, the increase k. I notice what it's doing here in the assembly file. So in this increase k here is supposed to accept 2 arguments. And now it starts to slowly unfold itself why we use 24 bytes, why we didn't use 4, right, or push. We needed a little bit more. We didn't maybe need 24, but maybe we need a little bit more. What we're doing here is that we're setting up the arguments for the next call. And we're doing it without calling push. In fact, we're doing what? Like, what exactly happens here? We put 3 into 4 ESP. So that's 4 bytes above where ESP is pointing. So that's the first or second argument? Second, right? Because the first argument just go in ESP, right? And that's what we do here. Here we get the effective address of, what is this? Remember this? The address of local address, right? And then we look here into EAX, and then we're going to move EAX into ESP. Remember, we don't have memory-to-memory operations, so we have to use EAX as an intermediate stop. So we're doing EAX, and then we move into ESP, and now we've put here 2 arguments in reverse order onto the stack. But we already allocated memory push, we didn't do push. And then we call increase k. Yeah, makes sense, right? I see one person nodding their head. I see 1, 2, 3 people asleep. And then I see people that are staring kind of expressionless into the wind, even though there's no wind. Okay? I'm hoping there's some people listening now. Okay, and then when we're done here, what do? We get the return value, which is in what register? Yeah, EAX, okay. And then well actually, there was no real return value from increase k. We're trying to create a return value. So in some sense, whatever was in EAX is going to be forgotten about because we've We've forgotten about it here in the C program. But we're returning our own, because we're at 3, we're supposed to return an integer. So we set up AIX to include whatever it is I want to do, which is local x. So we take the value for local x, remember our friend underscore equals b, move it to the AIX, and the return. There's an operation here called leave. What does leave do? Oh, hang on, let's do it. Leave pops EBP from the stack. It's just another way of doing it. This is a built-in instruction below. I'm sensing abundance of energy in this class. Anybody else want to hear? That's still waving. Yeah, okay. This will become more fun. I'm just going to set in the pillars for physics. Don't worry. So this is the second to last thing we're going to do in assembly. So in fact, we are doing 3 lectures worth of a full course on assembly. So this is supposed to be kind of like a lot of stuff. So if you're just like, this is fine, you're in good shape. Good. If you're like, I have absolutely no idea what's happening, bear with me. And this will all be online. So one of the things that we glossed over was these kind of compounded data types. Remember we had like just integers and possibly floats and so forth. But what if you wanted to have an array, right? And now that you've done Bomb Lab, you kind of have some idea about how arrays work, right? Some of the phases had something weird going on where they were using ESI and EPX from a 4 and all that stuff. And you're like, what's going on? And really what's going on under the hood there is that it's accessing arrays, right? So there's some assumption then that you can access sequential memory, and that is just a part of an array. So how do you actually represent arrays in memory? Suppose I ask for an integer array called A that has 16 bytes or integers. What does this mean? Yeah.
You have a pointer to the first address, then you just increment 4 every time you're trying to get
Right.
A2, A3.
In C, what does this give you? Does it give you 16 bytes of, therefore 4 integers?
That gives you 64.
64, yeah? So it gives you 16 integers worth of data. So it's 64 bytes in succession. Well, what about this one here? This goes malloc, which is allocating memory from the heap. We'll talk about it in detail how it works. This gets 256 consecutive bytes from somewhere in the heap, returns a pointer to it. Here we call it C. Okay? So remember the basic data types. Okay, we've already done this one. The basic data types are integers and bytes and characters and so forth. Now we can try to compound them together. So in general, if I declare an array in C, it's going to look something like this. It's going to be something called A or something. There's going to be a length, and there's going to be a type of T. So what I will end up asking the compiler is to give me a consecutive array or consecutive sequence of L times the size of my data type. So like 4 bytes or 8 bytes, whatever. So if I go char string 12, I'm asking for 12 characters. So I want 12 bytes in memory consecutive, and I want a pointer to the first one. And here, int val 5. What happened? This is 20 bytes, and I can reference them like this. If I want a double A3, remember what that was? A double was 8 bytes, we get like 3 of those, so 24 bytes. And what about this one here?
Array of pointers.
Okay, so I want 3 character pointers. And each of them 32-bit assembly is 4 bytes, 32 bits. So if I did the same thing on the 64-bit architecture, and then I've got 24 bytes of data. Okay? Cool. So, here's some, I figured you'd be asleep by now, so I tried to scramble and make some comedic impressions of walks. Anyway, so if I reference val of 4, what is the type of this thing here, and what's the value? Just suppose you get a what picture? Red. It's it's an integer. What's the value? It's a 3. Yeah. What's val over here? What's the reference? Int pointer, right? Int pointer, good. What's the value? X. Yeah. Okay. And val plus 1. What does this mean?
Add 1 to
Yeah, so does it refer to this byte over here or that one? X plus 4, because it's like in terms of integers, right? So it's what type is it though? It's an int pointer and it points to x plus 4. Okay, what about ampersand val of 2? It's another int pointer, because this is the address off thing here. So it's an int pointer, that's good. What's the value?
X plus 8.
X plus 8. Okay, val of 5 is an int pointer. What happens? Well, it's just an integer, right? What happens when I type in C that I want val of 5? It's fine, I don't care. Right? It's geo problem, no problem. So it's just going to be fine. So the value would be. Yeah, what about there? Okay, what about star val plus 1? Is integer in pointer? Sure. Int. I hear int. Int. Yes, that sounds good. What's the value of it?
1.
Yeah, 65. It's fine. Yes. So it's the second one over here. Okay. The val plus I is but generally still an int pointer, and the value is x plus x plus 4i over here. Okay, great. Okay, so what about an array here? So let's say that I want to make it a little bit more complicated. I create a data type here called zip date, which is just a 5 integer array. It's just a zip code written in 5 integers. It's just stupid, but very young. I will say that probably a lot in this class, just because I don't want to do something. So let's say that we have CMU, MIT, University of California, Berkeley. Here are the zip codes corresponding to the institutions, and then this kind of 5 integer arrays over here. Okay? So suppose they are located in memory like this. They're at byte 16, so forth, and then immediately after at byte 36, there's the next zip code, and the same thing for Berkeley. Okay? So when I type this down, when I say type def, really what's happening is that the preprocessor of C is going to look at it and be like, oh, zip take CMU. Yeah, you mean like in CMU 5, right? We have 5 integers there that are representing zip of CMU. There's no guarantee that these things are going to be actually aligned in memory. That these 3 zip codes are actually going to be consecutive. So the 36 over here could be entirely different. You might get misalignment so all the time. So if you think about now the operations that we have presented here in assembly, and you think about these arrays and the way we're representing them, now it starts to become a little bit more clear why we had this weird notation for address and direction. So the idea is simply there's some beginning of an array, and there's going to be some register over here, and then for instance we have like 4 element array of ints, right? So it's like 4 integers in a row. So I'm going to have some register here that's going to denote the start of an array. Usually it's like ESI, let's just say it's EDX for now. And then I'm going to have some offset, which is going to be how many integers do I want to go to, like go past to get to my index. It's my index. Wow, mind blown, right? So if I want to access an array, suppose this is my method over here. It's called getDigit. Gets the dict, how do you pronounce this? Dict digit from Z that you provide. So like the 3rd digit from that zip code over there, right? Let's look at what this looks like in assembly. So here's CMU, or whatever zip code over there in memory. And here's what the assembly code would actually look like. Really compact, very slick, right? Just take the base of the array, and then takes 4 times your index, and return that into EAX, because that's what you're going to return, and that's it. That's the entire implementation of this function. So natural, right? So, blah, 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 blah. This is what I just said. Let's look at it now in like an array look, for instance. Here we're going through every single zip code character, and we're adding one. Why? Why not? Okay. So let's look at what this would look like in assembly here. We have some array base. It's going to be our iterator over here, EAX. Start this from 0. We add 1 to this whole thing over here. Just look at this line. How much you accomplish in that one line of code, in the one line of assembly. You add 1 to the address that consists of register that has the array base plus 4 times the index. Voila. And then everything else is just boilerplate stuff, like add 1 to EAX. You could use the increase operation also. So you compare it to 5, like am I done with my loop? Well, I'm not done with my loop. I have to go back to label 4. Okay? An alternative way of doing this would be to use pointers instead of the for loop, right? So suppose it looked like this. There's some end point here. There's some way for us to terminate this loop. So what we're going to do, we're going to start with z as just pointing to the first digit, which is what an array always does. And we just increase what it points to, so the digit itself, and then we increase the pointer, so we go to the next digit. Okay? We're going to do this until we've hit the final digit. So z end here is just 5. What do you think the assembly code is going to look like for this? And how does it compare to the previous one? Well, lo and behold, this is what conversion actually happens under the hood, and you end up with this. Doesn't it look remarkably familiar? What is the difference from the previous one we looked at, the for loop?
The condition is to stop when it reaches 20 instead of the index.
Yeah, so why 20?
Because counting, like,
Yeah, 1 byte at a time, right? Which also means that we don't have a 4 thing over here. We have to multiply this by 4. And how do we do that? Yeah, by increasing it by 4 every time instead of 1. It's just everything's scaled by 4. Everything else is identical. So in other words, pointer arithmetic in C and actual arithmetic over arrays in C almost looks the same at the assembly level, for good reason. Right? So there's some duality between pointers and integers. Now you can like lock yourself in a room and write a poem away. Now here's another question. How do you fit a 2D array into memory? Suppose we have this 2-dimensional array here, it's a 3x3. And you have to make a choice. How are you going to take this 9 things over here and put it in memory? At random is incorrect. Sorry?
An array of arrays?
An array of arrays. So, but columns or
That's the first entry.
could take diagonal.
Whatever you feel like?
What?
Whatever the compiler feels like?
Yeah. Like today, I'm row major. I'm really row major today. And then when you like execute it later, it's like, yeah, I just don't feel like it today. Just gonna have excessive like call it. So it's okay to make an arbitrary choice here. And for whatever reason, they chose that it should be a row major notation. So you take the rows here and like, split them down into here. So they're going to be consecutive in memory, but row by row, right? Now, if that's the case, how do we traverse or find an arbitrary cell of a 2D array? Row major array. So I want to find cell ij. So here's a graph picture. My favorite graph picture all time. Yeah. Anyway, so it's probably a dunk meme by now. So here's another way to express what we're doing. This is our 2-dimensional array. It's a bunch of zip codes together, right? So zip codes in kind of an array structure. So it looks like this. We have a first zip code, and then immediately following that, there's the next one, and so forth. We're guaranteed that there's going to be some level order. I want to find cell I, j. What is my formula for finding cell I, j? Given. Well, let's start with something slightly simpler. Let's just try to find the correct row, right? So recall that we could think about the zip code stuff as just being a 2-dimensional array. So I could actually write int EGA 4, 5. And it would say it's 4 5-element integer arrays. So 1, 2, 3, 4. Okay? So let's say, here's the more general notation for that. So this is our duplicate array, we have our type, we have our row, we have our columns, and so forth. We will keep going, we can have multi-dimensional arrays. And we're going to need k bytes for every single cell. And k here would be something like 4. It's the size of this thing called t, right? Size of t. Right. So we're going to int a RT over here. So now I'm going to take this beautiful yellow thing over here, and I'm just going to change it into what C uses to refer to different variables. So the top left corner is going to be A00, and the bottom right is going to be A of R-1, C-1, right? You can start counting from 0, and so let's do the last one over here. I'm still looking for a formula to find the cell I, j. Right? So let's look at what we would need to do. If I'm standing right here, at the beginning of this array over here, every single little cell over here is k bytes. Right? How do I find cell I, j?
Do C times K plus R times 1.
It's something in our order, right?
R times Y.
plus C
1 plus C.
times the size of T times K.
Yeah. Or the sum of all this suggestions. Right? Maybe average? Geometric average. Okay? Yeah, something like that. I think you can kind of, if you stare at it for a few seconds, I'm sure all of you can figure it out. Let's just do it, okay? So let's just start by figuring out how to get to the row. Well, we start by the array base here, which is capital A, and we have to walk past a bunch of rows. How big is every row in memory?
C times
Yeah, C times K. There's C columns, and there's K for each cell in there. And I have to do it if I want I of these, I have to do it I times. So C times K, right? So in other words, here's A, here's my arbitrary row that I wanted. This address over here is going to be I plus I times C, sorry, A plus I times C times, in this case, 4, or K. Okay? And now I wanted to find the jth element of that row, this J column there. So I just add J times K, right? So, oh. Yeah, here. So this is the first one, and that's the second one. So if we look at the assembly code over here for finding two-dimensional axes, we're going to look at finding, well, actually here it's just doing a computation of 5 times index, and then it's going to add that. So this is how you would access the indexed element of an array here. So we found the general purpose over here. So in other words, the cell that's located at ij is at this location here in memory. Okay? You remember the tattoo from that earlier person? Yeah, that's that one, just slightly wrong. So, that actually covers everything I really wanted to teach you about assembly. This is the right time for questions. I'm sure you're all done. Like, oh, yeah, go ahead.
Why isn't memory green? You did that with other titles.
Why is it green or why is it not
Well,
green?
why is memory not green, but like PC programming, you have to register file, condition codes are green?
The whole thing is kind of supposed to be green. So, oh, you're saying that because of the second order subtitle over here,
Yeah,
yeah?
why is it inconsistent?
I'm going to take this as kind of like a latent, passive-aggressive criticism of my PowerPoint skills, which I'm happy to discuss. Is the unit forward on the slide bugging you, or is it the OCD that's kicking in? No. It is probably supposed to be here. At 1 a.m., when you're scrubbing to make a lecture, you may not have noticed this little red dot over here, and you thought it was like a primitive thing here. This is not true, but yeah, it's supposed to be green. Yeah. Any other passive-aggressive comments? Don't hold back. Or just write me an anonymous note. Next time, make sure you put everything green. More comments? Happy to receive any type of comment.
I have a question.
Yes.
Okay, so, back to when we're talking about stack frames.
Yes.
Color frame. So, I noticed that like when you're changing in functions, it'll add massive
Huge
number
amount,
of
yeah.
stack pointer.
Yeah.
And then there's all this extra room.
Inflation.
So why? What's the purpose of that?
So I've been trying to find the the actual answer to that question, because yeah, there's a compounded number of reasons for it. The biggest reason is alignment of the program, right? And the alignment has to do with the fact that if you think about how operations happen in your CPU, you're retrieving your program as any type of data from memory, right? And if you're retrieving it, you're actually trying to retrieve a little bit more than what you're doing, because you think that things are going to go in sequence. You're thinking about the locality of access, right? So you actually retrieve that whole stuff, you put it into memory, and you want to make sure that it's aligned enough so that when you're executing things, you're not trying to do special instructions to kind of like, let me get the third byte from that structure or nothing. You want something that's kind of more working at the 8 or 16 byte boundary and so forth, because it's more efficient for the CPU to work with those operations. So the part of the compiler optimization framework is trying to make sure that those things are aligned like that, just to make all the operations simpler, to make cache checks more clean, and therefore to make everything faster. So that's the kind of long-winded answer. It's kind of it's the mechanical output of a very complex optimization problem that's being solved by both the CPU as well as the compiler that results in this ridiculous size stackers.
Okay.
Now that's one part of the answer, and I think there are more parts to it. One of them I think is just pure gluttony. It's like, why not 2,000 bytes, right? And then don't use any of them. Why? Well, I don't particularly know. Sometimes I look at it and be like, that is so absurd. Like, that's like extortion, right? It feels like you're dealing with Bank of America or something, right? It's like really, like, I don't understand the full reason for it, but at least alignment is the part of it that's very clear.
So it's not something we should be expecting to.
No, I won't. No, I'll put it on the exam, of course. But previously I wasn't going to. More questions? No, I actually, this is a great question. I'll try to look up a bit more parts to answer that. Shouldn't be disturbed. More questions? No, okay. So stay tuned for several things. One of them is possibly change in classroom to an alternate location, which has not materialized yet. I haven't seen any updates on that. Maybe they'll be moved to one room adjacent. Keep up on Piazza. Feel free to ask questions. It was very lonely there for both me and Aaron. We were just there with like a big bowl of popcorn, like nobody asking questions. Feel free to ask questions. It's fine. It's supposed to be fun. There will be a buff lab coming out, hopefully tonight or something like that. It will have a similar kind of a PDF explaining what on earth you're supposed to be doing. I've updated Piazza so like there's a shared Google Drive that has these PowerPoints that you can access. So like when I make them, they're going to be in the folder, so you can just see it right away. There's a YouTube playlist that automatically adds videos as I upload them. So you can see the most recent videos, but you also have access to the previous playlist of previous incarnation of this course. So you can scout ahead, and you can like get all the answers. You can go into class and be like, oh man, it's like EPX or EPX, yeah. Or do whatever you want with it. Other things to look forward to. Yeah. Office hours today at 1 if you want to show up. And Aaron is hosting something on Fridays. I think he's made a post about that. Right? Any questions before we close? No? Cool. Okay. See you on Monday. Or at 1.